So hello everyone, welcome back to the another lecture. So my name is Ashish and today we will be in the lecture number 3, that is single phase shift modulation in the DAP converter. Okay, so in the previous class we have seen that how the power is flow from one bridge to another bridge, then which parameter is important to flow up power from one bridge to another bridge, right? So this thing we have seen. So we understood that okay, so the phase angle between the primary bridge and secondary bridge is the responsible for power flow. Then how the phase angle we are going to give by adjusting the this gate pulses. Then based on how the gate pulses are given in between the two bridges, we have defined the several modulation techniques like the single phase shift modulation, double phase shift modulation, triple phase shift modulation, then trapezoidal modulation, and then basically triangular modulation. So all these modulation, how to implement, that part we have seen. Okay, so we have seen that what is the gate pattern for all this modulation scheme. Now next task what we need to do is we need to analyze each modulation techniques in detail, like after giving such a gate pattern what my circuit will be work, how the circuit will work, what exactly the behavior of the IL is. We have our certain objective for the adapt converter to use the different modulation techniques. So what are those objective I have stated initially is like we need to reduce the peak current of IL because we don't want the IL to have very high peak current, and if the IL to have very high peak current, then I need to design the value of the IL in such a way, right? So that is the first thing. Then second thing for going for different modulation techniques is to have the soft switching. Okay, because in single phase shift modulation there is a basically narrow window where mostly soft switching will happen. What is that window and all these thing we are going to cover. Okay, so as of now we will start with the single phase shift modulation in the DAP converter, where we will going to learn in detail about how the single phase shift modulation operate and what are the different expression how we can derive. Okay, so all these things we are going to cover in this lecture. So let's get started with this. So here we are in a new window where we are going to learn the single phase shift modulation technique. So this is my DAP converter. Okay, and in the last class only we have understood that when in a bridge B1, basically when S1 and S4 are on and S2 and S3 are off, what is the my VT1? Okay, when S1 S4 are off, S2 S3 are on, what is my VT1? So this thing we have seen. Also at the same time I have emphasizes on the direction of the IL as well. On similarly in bridge B2, if Q1 Q4 on, Q2 Q3 off, Q3 and this is Q3. Okay, so this is my Q3. So if the Q3 is off, what is my V2? So this thing we have seen. Also Q1 Q4 off, Q2 Q3 on, then what is my V2? That is minus of V2. So these thing we have seen, and direction of the current what is there at that particular time, this thing we have seen. Now for the single phase shift modulation, I told you that this is the pattern of the my gate pulses. So S1 S4 are turned on at the same time and S2 S3 are complementary to S1 and S4. Then Q1 and Q4 are turned on by some adjusting the some angle in between them, which is called, I am calling it as a delta, and this is my phase angle, or I can call it as a displacement angle for S1 and Q1. Okay, then Q2 and Q3 are complementary to Q1 and Q4. So now I am providing the single basically phase shift, so that is why its name is called as a single phase shift modulation. Now based on this I need to analyze my circuit very carefully. Now we will start with analyzing the first waveform, that is a VT1. So what is a VT1? I am going to explain you. So when S1 and S4 on, so we are here at this particular instant. So when S1 and S4 on, so we know that when S1 and S4 on, VT1 equal to V1. So what I have drawn here at this particular instant, you can see here, like I am here in this particular expression in this particular zone. So I have drawn VT1 as equals to V1. So you can see that in between these particular points, so we are at V1. Now once S1 and S4 are off, now what basically turn on in this particular bridge, that is the S2 and S3. Now S2 and S3 are on. So what will happen? What is my VT1? I wanted to know. So this is also we know when S2 and S3 are on, my VT1 is minus of V1. So can I plot it? So this is my V1. Now suddenly my waveform will shift from plus V1 to minus of V1. Okay, so I am here at minus of V1 and this will be there till up to particular what point, unless S1 and S4 again turn on. So initially it is plus V1 and then it is goes to minus V1 and it is minus V1 for some duration, and then again it will become the plus V1 when S1 and S4 are on. So we are pretty much clear what is the waveform of VT1. Okay, so this is the nature, and this is one more thing, important thing is here what we will do generally is that we will assume the duty ratio as 50%. Okay, so duty ratio I am marking D here. Basically I will mark it as small d, don't confuse between capital D and small d. Okay, so capital D we will use somewhere else. So basically this we will use generally as a 50% pulses. Okay, so for 50% duration we will turn on the S1 and S4, and for 50% duration we will turn on S3 and S4. So that is why I mark it as 0.5 TS. So basically plus plus V1 voltage is there for 0.5 TS, and minus V1 voltage is there for 0.5 TS, and this will complete my TS overall time period, and TS is nothing but the 1 upon FSW. Okay, so I guess what is the VT1 that we have understood. Now what is the VT2 I wanted to know. So VT2 when refers to primary side, what it will be, so it is the n times of the VT2. So you know that V2 by V1 is equal to N2 by N1, and N2 by N1 is my 1 by N. So from this can I calculate what is the voltage that come appear across this? Yes. So that is the n times of V2. Now I wanted to calculate this voltage. So for calculating this voltage, what I should know, like when Q1 and Q4 on, I should know what is the when Q1 and Q4 on, V2 equal to VT2. So VT2 is equal to the V2. Similarly, when Q2 and Q3 on, VT2 is equal to minus of V2. I can easily say. Now the same thing I am going to basically draw here. Now you can see that when my Q1 Q4 on, so this is the point where Q1 Q4 on. So from this particular point, can I draw it as basically a V2 or n times of the VT2? Yes. Why it is n times of the VT2, or I will not n times of the VT2 is my the waveform which is coming here, and what is its magnitude? N times of the V2. So this is the particular waveform n times of V2 I am going to get here, right? I am referring all the parameter to primary side. Then when basically Q1 Q4 on, till that time it is n times of the V2. Now as soon as the Q1 Q4 turns off, what will happen? Q2 and Q3 will turn on. Now when the Q2 and Q3 will turn on, its voltage is what we know, when Q2 and Q3 turn on, so V2 equal to minus of, so it will goes to negative direction. So what it is? Minus of n times of V2. So for this particular duration when Q2 and Q3 are on, its voltage is minus of n times of V2, and then again it will goes to n times of V2. So this is how we can easily draw the waveforms of VT1 and VT2. Till this point I guess everything is clear. Now we wanted to draw the waveform for IL. So what is my VL? I wanted to draw the waveform for VL. What is VL? VL is my VT1 minus n times of VT2, minus n times of VT2. So using the simple KVL I can write it down this. Okay, so n times of the VT2. So this is the waveform. So now VT2 is at this particular point and VT1 at this particular point. So I can easily go here and apply the KVL, so I can get the voltage across the VL. Now VL waveform will determine what is the waveform of IL. Okay, so IL I have already drawn, but what is the VL waveform? VL waveform will determine what is the IL waveform. Okay, so now we will try to draw the VL waveform. So VL is just basically a subtraction of VT1 and VT2, minus n times of VT2. Okay, now when I will do that, what I am going to get here, just try to see here. So my I will start from this particular point. Okay, so I will start from this particular point. What is my nature of the waveform? Okay, so there my initially during this particular phase, when there is a basically angle of delta, so my V1 is positive and this is negative. So overall what I am getting, this V1 plus basically minus of minus what, plus, so V1 plus n times of the V2. So I am getting some voltage here initially. Okay, then V1 is here and n times of. So another assumption here we are taking is that V1 is greater than basically n times of V2. Okay, n times of V2. This is what I am considering here. Okay, So there are different cases when V1 less than n times of V2, so that time waveform will be different. Okay, but here for understanding purpose I am assuming that V1 is greater than n times of V2, and based on that I am going to basically draw my overall circuit. So initially what I said, in this particular time period V1 basically always greater, V1 minus of minus n times of V2 is overall V1 plus n times of V2. Then here V1 and here is again n times of V2. So V1 minus n times of V2 and V1 is greater. So basically my voltage will drop, and some voltage I am getting in this particular point. Next to that, what is there? This is my minus, okay, and minus of this. So again it will go at some larger value, right? So I will go basically at the bottom. Then for this particular duration again overlapping is there, very short. So again I am getting some voltage, and then this particular V1 minus of this, to minus V1 minus of minus n times of V2, so it is coming some again voltage, right? And it will be again, and then the periodicity will be start again. Okay, so what is the voltage at this particular point? So the voltage at this particular point is V1 plus n times of V2. What is the voltage at this particular point? V1 minus n times of V2. What is the voltage at this particular point? Minus of V1 minus of n times of V2. What is the voltage at this particular point? Minus of V1 plus n times of the V2. So this is the values, and basically this will repeat again. So this is how we can draw the basically V1 waveform. Okay, so I guess you understood how we draw, how we subtract the two waveform, and we get the VL waveform. Now from the VL we need to draw the waveform of the IL. So basically you know VL is nothing but what? Basically VL by L is nothing but what? VL is equal to L di by dt. So it is a di by dt. So we have the value of the VL, we just need to divide it by the basically L, then we will get the slopes, right? VL by L, this particular thing is my di by dt. So we have the slopes available with us. So what is the slope of this? We know what is the voltage here, V1 plus n times of V2. So what is the slope here? V1 plus n times of V2 whole divided by L. So that is a very simple thing. Okay, now let us start with some particular value. Okay, so we are starting with some value here. Okay, at this particular value let us assume that basically some particular initial voltage is there, that is a minus of I peak. So now the slope is positive here, my overall both the voltage are basically overall additive. So what will happen, my current will start basically increasing. So now it is started increasing, and it will increase up to what particular value, this particular value. Okay, when it is V1 plus n times of V2. Once that is done, my voltage is fall. So what will happen, overall slope will be decreases. So what is happening now, it is what, V1 minus n times of V2. So voltage is now basically not that sharp, it is slightly increasing. So this is the first peak which we get for inductor current, this is the second peak which we get for inductor current. Now after this particular point my voltage is dropping, right? And it is basically minus of V1 minus of n times of V2. So again with that much of high slope, it is basically sharply decreasing till this particular point. Okay, I have drawn it here something wrong, it should be up to this particular point. So up to this particular point it is decreases, and again when we come here, what is the value, minus of V1 plus n times of V2. So again very small what I will say, small still slope is there. So with that particular slope it is decreasing. Okay, and then again it will start increasing in the same way where it is started. So this is how the waveform of IL we can draw. Now for any modulation scheme you can able to draw the waveforms for VL and IL. You know how the switching patterns are there, right? We will draw in future as well in upcoming lectures, but now it's your responsibility that okay, you know this how the gate pulses are given to the switches, and based on those gate pulses how we can basically draw the V1 and n times of V2, and based on that how we can drawing the VL, and based on that how we are going to draw the IL waveform. So how to calculate the IL waveform you know now. Okay, now here I have marked some reasons, like this is the one reason, this is the one reason, and this is the one reason. So when what is those reason are called as, those are called as backward power flow reason. What I am saying is that backward power flow reason. What is that term? Just keep in your mind this region we call as a backward power flow region, and what is exactly the meaning of this we will learn in detail in the few next classes. Okay, just keep this term in your mind. Now I have marked some region here, like let us say this is my T1 time, T1 to T2 there is a backward power flow, and T2 to T3 there is a basically some increasing slope, and overall this duration my delta, where basically my overlap basically happening of the switches. Okay, or I would say this is a phase displacement which is happening in the two bridges, that is a phase shift. Okay, and this is the overall duration from here to this particular point. This is my overall TS. Okay, so this is how we have drawn the IL. Now I wanted to draw the I2. So what is my I2? This is the I2. We know that when I2 is equal to IL, I2 equal to IL when Q1 and Q4 are on, and I2 equal to minus of IL when Q2 and Q3 are on. So based on that, can I draw the waveform of IL? Yes, I can easily draw. So let us try to draw this here. So I will start with this particular point. Okay, so from here I will just try to draw for you. Okay, now what is happening in this particular duration, you can see that which particular switches are on. Q1 and Q4 are off, and Q2 and Q3 are on. So what I know, when Q1 and Q4 are on, I2 equal to minus of IL. So here IL is there with the increasing slope, so it should be negative of that. So it will start with some value and it should fall. So this should be happen. Okay, in this duration. Now after that, in this duration, what you can see is that Q1 and Q4 are on. When Q1 and Q4 are on, I2 equal to IL we know. So it will try to have the same slope. So it will quickly go at the top, and it will try to be same. Okay, this is how. Then again, what is going to happen once that is done, then you can see that here again after this particular point, this is the this point. After this particular point, Q1 and Q4 are again on, so I2 equal to IL. Then it is decreasing nature, so it will also try to be the same decreasing nature. Okay, like here. Then again this particular point will come where this is the negative slope, and at this particular time Q1 and Q4 are off, so I2 equal to minus of IL. So it is now decreasing, but what actually it will see increasing, because I2 equal to minus of IL. So again this particular slope, and this will repeat. So you can see that if you see this particular thing, it's what is the time period. So its time period is TS by 2. So this waveform is repeated after the time period of TS by 2, because it has a symmetricity. So the overall time period of this waveform is TS. Okay, because it is basically repeating from this particular point to this particular point. It has a time period, and after this interval it is started to repeat. But what is the waveform of I2? I2 is basically repeating after the TS by 2. So this is the waveform of I2 we have got. Okay, so maybe I have drawn something not too perfect, but at least you understood that how we have drawn the I2 waveform. Once I2 is drawn, you know that this is I2, then we have put the one filter capacitor there. So what is the value of the I0 which is going to get here? So I0 will be constant. So rectified version of I2 basically is my I0, which will be the some constant current. Okay, based on my load current. So up to this point, I think we are good to go for the next point. So I guess you have understood that how we have drawn all the waveforms and all. We have took the D is equal to 50%. That is also we understood, and basically we understood that how we have drawn the VL, how we have drawn the IL, and how we have drawn the I2 waveform. Now why I have drawn the I2 waveform? Because I need to calculate what is the power transfer from bridge 1 to bridge 2. That is my ultimate motto, and I told you that what is I0. I0 is basically rectified version of the I2. So that is why if I have the waveform of I2, I can easily go for calculation of the power. Now we will took this particular waveform, and we will try to analyze the power calculation. Okay, so this is the same I2 waveform I have drawn here. Okay, now I2 waveform you can see on your screen. So I have marked some initial things here. So let us say I have just shifted the waveform, just we have started from here. So now I am assuming that this is my 0 point. So it is started with some value, I marked it as a IB value, okay, and then it is decreasing. So the point when it reaches the 0 point, I marked it as a T1, okay. So these waveform are for basically just understanding purpose how the operation is happening. Now we are going in a derivation form, okay, how to derive the power transfer expression in the single phase shift modulation, okay. So this is the waveform which I have took, and now we will try to analyze this. So what I said, so it is started with some IV value, and the point when it touches the 0, I marked this particular interval as T1. Then again it will be decreased, so it will decrease up to the point of IA. That is the second instant. I have marked it as current of minus of IA. Then this waveform goes to IA, and again it will goes to the IB. So this particular point to this particular point, what is the distance? Ts by 2 minus delta, because overall time period is Ts by 2, right? And this delta duration is there, that is my basically single phase shift, okay, which we have provided. That's the delta I have marked. Now I wanted to, and I am considering here it as n. Small n is my n2 by n1, which is 1 by n, okay. So now I am not going to use the n, I will use the small n, okay, for my overall derivation. So I need to calculate the value of the I naught, because I know that power is what? Power is what? Power is output power. If I wanted to calculate, output power is V2 into I naught, right? So if I know the I naught, I know the V2. So V2 into I naught is my overall power. So that is the thing I am trying to calculate now. So what is my I naught? I have written down here. I naught is delta Q divided by, so you know that IT is equal to charge. I into the T is nothing but the Q. So this is the basic expression you know. And from this particular expression, we will try to derive over I. So I naught is equal to delta Q divided by N into ds by 2. Why I have written down here N? Because I will try to have the values with respect to the primary side inductance, right? So that is why this N term is there, N into ts by 2, and overall duration of the curve which I am going to take is ts by 2. Now what is this delta Q? So I have marked in the figure like the three regions. So if you see this particular I2 curve, there are the three regions, like three triangles. So this is first trapezoid, then second this one, and this a small third one. So this is just same as this particular one, right? So three things are there. So the first area plus second area minus this third Q3 area will give me overall Q delta Q. This is very simple thing, right? So from the area calculation of this curve, I am going to derive my expression. So what is my delta Q here? Q1 plus Q2 minus Q3. So I have marked these three regions. Now we will try to formulate some relation. What is the IA? Now you see that this current IA is there. Okay, so this IA current is there. So what is the slope we know at this particular point? What is the slope? So slope will be V1 plus V2 by N whole divided by L into the T2. So IA is starting from this particular point, okay, or you can take some different IA. Okay, this particular IA we can take. So this particular point to this particular point, so IA is T2 into basically V1 plus V2 by N whole divided by L. So very basic maths we are applying. What is IB here? So if I wanted to calculate the IB touches here at this particular point, and IA touches in between this particular point. That is why the T2 is there. Now IB is basically T1 into V1 plus V2 by N whole divided by L. What is the slope of this line? We know it is, you are seeing it as a downward slope, but we know that that particular time my Q1 and Q4 are off. So I2 is equal to minus of IL. So that is why it is V1 plus V2 by N, right, and whole divided by L. So IA and IB expression we understood, very basic fundamental. Now I wanted to know what is the area of this particular triangles. Now first is a Q1. Q1 is a trapezoid. What is the area of the trapezoid? So this IA plus IB multiplied by what is this particular time? Ts by 2 minus del whole multiplied by 1 by 2. So you know the area of the trapezoid. So the same formula I have written down. What is this particular small area? What is its base height? So half of the base. So base is basically what? This is my T1. So this is the same area which is there. So half of the base into height. So half of the T1 into IB. What is this particular? Half of the base, that is my T2 into height is my IA. So these three expression we have tried to write it down. So Q2 and Q3. Now we have all the expression, and can we put this particular value in delta Q, and can we proceed further? Yes. So I guess this particular maths you understood from this particular waveform. Okay, you are good in maths compared to me. I just have to give you a hint how we are proceeding. Okay, now few more things I have tried to calculate here, like IA plus IB. So if I wanted to calculate the IA plus IB, what is the IA, what is IB, we know, we have found out. Then IA plus IB, can I write it down? T1, so just I have added then T1 plus T2 multiplied by V1 plus V2 whole divided by N whole divided by L. And what is T1 plus T2? So this T1 plus T2 duration is delta, so delta into this particular term. Then I have tried to calculate the IB minus IA. So what is IB minus IA? So there might be the two expression I got. So IB minus IA, if I will do, I will get basically TA minus T2 whole multiplied by this particular term, okay, which is a common. What is the other way to write it down, the IB minus IA? So you can see that this is my IB and this is my IA. So can I write it down IB minus IA? Yes. So what is this particular duration? It is TS by 2 minus del. So this is this particular duration. You can see easily, right? So this is basically delta duration. So Ts by 2 minus del, and at this particular time, what is the slope? V1 minus V2 whole divided by N whole divided by L. So from here I have written down IB minus IA. Now I have just substituted the value, and this is all pure maths. You can do this maths by your own as well. So I am just showing you what is maths we have done. So you can just quickly have the screenshot, or if you are noting down the things, you can just pause the video and try to took the notes. So I have just tried to put the value of the Q1 and get the some expression, try to put the value of the Q2, get some expression, try to put the value of the Q3, get some expression. Then overall delta Q I know, so I have just put it the values and I got some sort of this term. Then I use the some identities, and whatever the expression we have written down at the top, the same expression are written at the bottom, and try to solve this. And once I have tried solving it and try to compute it, I got some value of the delta Q, which is V1 into delta whole in bracket Ts by 2 minus del whole divided by L. So this is the expression I got. Okay, so I guess you can just took the screenshot. So what is ultimate motto of mine is to basically have this waveform with us, how we are writing down the expression. So this is the very foundation thing which you understood. Okay, when you do it for the other modulation technique, at that time all these things are very helpful. Okay, how we are writing down the things. Okay, so just keep in your mind. So we have come up with one expression for delta Q. Okay, this is pure maths. I hope you will understand just by basically seeing these particular things. If you have any doubt, please ask me. I will try to answer in the comment. So now once we have the value of the delta Q, it is very easy for me to calculate the I naught. So I naught we know, delta Q divided by N into Ts by 2. So I have just put it the values and I got the expression for I naught, which is my output current. Now we generally don't use the delta. We will use some normalization duty shift, normalization duty slash shift ratio, which is called as a D factor, and that D factor is del divided by Ts by 2. So instead of del divided by Ts by 2, I am going to use the term D, and when I will keep that term here, I am going to get the expression for I naught, which is V1 into D in bracket 1 minus D divided by 2 ln Fs. Okay, so this is the formula for my I naught. Now from this particular formula, I naught is nothing but what? I naught is nothing but the V naught by R. We know that, right? So V naught is my what? V naught is nothing but the V2. So from that I will get some output voltage ratio, V2 by V1 I can calculate. So V2 by V1 factor I can calculate from this particular thing. Now why we do all these things? To derive the expression of the power. So now output power P naught delivered to the secondary or load is what? P naught is V2 into I naught, that I told you. We know the formula for I naught which we have derived, and when I keep all the things inside the formula, I am going to get this particular overall expression, and this is a well-known famous expression for the single phase shift DAP converter. This is what? P naught equal to V1 into V2 divided by 2 NLFS multiplied by D in bracket 1 minus D. So this is the overall expression which we are very much interested. So this is how, by changing this D value or delta value, we can have the different power for different particular delta. Right, so this is the overall expression. So how we started this video? We started with this video with this particular simple DAP converter operation. Then we have this particular basically gate pulses. We know this sequence, right, for single phase shift. and then from this we try to come up with the waveform for VL. Okay, I hope so. For the different modulation techniques, you will draw the VL waveform by your own. In the same way, we have tried to come up with the waveform for IL, and what is the waveform from I naught we have come up. Okay, then we took this waveform of the I2, which is a basically, again, if we rectify this, I am going to get I naught. So with the waveform of the I2, I have tried to calculate the area required. I have tried to calculate the I naught value, which is delta Q by n times of ds by 2. Same kind of thing will come in every expression, but only difference will that what is this delta Q and all will change. Okay, so and then again it is a pure maths which you need to understand. Okay, so I have tried my best to explain the things. If anything you think that this is something wrong, or this might I have missed to tell, you can just comment it out. I can try, I'll surely reply. Okay, and then we have derived the output current expression, and finally we have come up with the formula for P naught. Okay, so this is all for this video. I guess this is a bit of long video, so that's why I'll pausing here. In the next class, I will make a part 2 of this video, where we will derive a very short video where we will talk about the maximum power transfer in the basically this single phase shift. So what is the maximum power that I can transfer in single phase shift? Also, what is the at what particular value of the D I might get the maximum power? Based on this particular expression, there I will try to explain you what is the constraint on L. What is the value of the L I can take? What value we should take so that I can have the maximum power? So all these things I will try to explain in the next class. So that will be very small video, but very informative. Okay, based on that video only we will try to go for the design calculation. Okay, so with this I will stop here. Thanks for watching, and see you in the next class.